This animation is a reenactment of a tragic workplace accident that resulted in 1 fatality and 1 serious injury. The animation presents the chronology of events leading up to the accident and is made solely for the purpose of transferring knowledge and learning. The accident occurred on 7th December 2017 on the Maersk Interceptor, a jack-up offshore drilling rig operating on Aker BP's Tambar field on the Norwegian continental shelf. The accident happened when a sling used in a lifting operation failed, causing a raw water pump to fall to sea, resulting in 1 person suffering a fatal fall overboard and 1 person suffering serious injuries. The Maersk Interceptor is fitted with 6 submersible raw water pumps, 2 in each leg. The raw water pumps feed raw water into a pressurized ring line, supplying seawater to all subsystems on board the rig. The raw water pump is fitted with a 150-meter electrical supply cable spooled onto a cable drum. At the time of the incident, the cable drum was mounted on a temporary support frame on top of the rig's ventilation house. On the day of the accident, workers were in the process of reinstalling a raw water pump after corrective maintenance had been carried out on the pump. 2 workers were tasked with feeding out cable from the drum to create some cable slack for the pump running operation going on beneath them. The raw water pump and risers are installed inside the leg well, where 3 riser guides keep the pump in the correct position as it is lowered down below the water surface. Installation of raw water pumps and risers is done using an 18-ton trolley hoist mounted on a horizontal trolley beam. The trolley hoist can move horizontally along a trolley beam. The trolley beam is designed with a skidding arrangement, enabling the trolley beam to move in and out. However, due to the location of the 3 riser guides, the trolley beam cannot be skidded out far enough to create a completely vertical lift of the raw water pump and risers. On the day of the accident, the work team comprised 4 workers. The 2 workers on the ventilation house feeding out electrical cable from the drum, and 2 workers at the worksite lifting and installing the raw water pump. The work was carried out under a work permit. The handling procedure for raw water riser was enclosed with the work permit. However, this procedure did not cover the actual installation of the raw water pump. Generally, when planning a critical work task for which there is no procedure, a safe job analysis should be conducted. But in this actual case, the need for this had not been identified. A toolbox talk was conducted prior to the start of the work. However, because the work team saw the work as a maintenance task and not a lifting operation, the required lifting operations planning was not conducted. At the worksite, the task leader was controlling the remote control of the trolley hoist. Since the lift of the raw water pump was not a straight vertical lift, the other worker needed to push and guide the pump over the hull side and in between the riser guides. The securing of the electric cables is essential for passing through the splash zone and to cope with vibrations during operations, as otherwise cable failure is likely to damage the electrical motor and cause the pump to malfunction. However, the 2 electrical cables coming out of the pump did not fit into the inlay for the cable holder. This had led to the removal of the cable holder latch and a normalized practice of using cable ties to secure the cables. As the pump was lowered, some of the cable ties broke. This was noticed by one of the workers, who signaled for the pump to be raised again to replace the broken cable ties. The pump section weighed 2.9 tons. With an offset angle of 1.7 degree on the lift, a force of around 100 kilograms was required to move and keep the pump away from the hull side. Normally, a person is able to push half their body weight when pushing steadily at shoulder height, meaning that it would require 2 to 3 persons to push and hold the pump clear of the hull side. The worker recognizes that he is not able to push the pump on his own. One of the other 2 workers, who by then had arrived at the worksite after completion of their work scope, steps in to assist in pushing the pump. The pump is still too heavy, so the task leader hands over the remote control of the trolley hoist to one of the workers and steps in to assist. With 3 workers pushing the pump, they managed to push the pump clear from the hull side, allowing it to be lifted high enough to access the broken cable ties. What happened? As the pump was raised high enough for access, one of the workers turned to get new cable ties. At this time, the pump had hung up on a protruding edge of the hull side. This caused the flat-braided wire sling used to lift the raw water pump to part, resulting in the pump and the connected cable falling down through the leg well into the sea. The consequence? One person suffering a fatal fall overboard and one person suffering serious injuries. An investigation into the causes of the accident was conducted. The following is a summary of the factors found to have contributed to the failure of the sling and a review of the barrier elements which on the day of the accident were ineffective. To understand why the sling failed, the following 3 key concepts are important: braking strength, safety factor, and working load limit. Braking strength is the rated capacity of a sling, meaning the force at which a sling is expected to brake. For the sling type used when the accident occurred, the braking strength was 24 tons for a straight pull. However, a safety factor is applied in determining the working load limit of a sling. For the sling type used when the accident occurred, the applicable safety factor was 5. Resultantly, the sling's working load limit for a straight pull was 4.8 tons, and with the rigging configuration used, 9.3 tons, resulting in an expected braking strength of 46.5 tons. Then how could a trolley hoist with a capacity of 18 tons brake the sling? The investigation found that a number of factors contributed to this. The slight tilting of the pump section when it hung up on the hull side created an uneven loading of the sling, resulting in significantly more pulling on one leg of the sling than on the other. The small radius of the crane hook load-bearing surface resulted in the pulling force being applied to a very limited section of the sling, thereby reducing the strength of the sling. The fracture patterns on the failed sling indicated that the sling was twisted over the crane hook, reducing the strength of the sling. These factors collectively are likely to have reduced the capacity of the sling to below the 18 tons of the trolley hoist. Having looked at what factors caused the sling to fail, let us examine some of the ineffective barrier elements that allowed this to happen. The investigation revealed ineffective technical, operational, and organizational barrier elements. Technical barrier elements. The design of the raw water system required an offset lift and had inherent snagging hazards in the lift path. To manage the 1.7-degree offset on the lifting angle, workers were required to apply force manually to the pump section to move it out and away from the hull side. The risk and barrier management process conducted when designing the unit had not contributed sufficiently to ensure safe design and operation of the raw water system. Operational risk assessment in equipment design phase is essential to provide safe design solutions. Operational barrier elements. The material handling plan for the rig only covered the handling of raw water risers, not the pump section. 3 other operational procedures related to the raw water system existed. However, none of these covered the specific handling of the raw water pump section. Given the absence of an applicable procedure, taking into consideration the complexity of the work, the need for safe job analysis should have been identified during the preparation for the work. However, the existence of several documents covering the raw water handling operations introduced ambiguity and unnecessary complexity, making it difficult to identify the applicable procedure or, as in this case, the absence of one. If risks are not adequately identified and controlled through applicable procedures or work permit, a safe job analysis must be carried out. The capacity to stop and reassess the situation when a job changes is essential for safely managing complex work in an ever-changing offshore environment. A number of changes occurred during completion of the work compared to the original plan, but the job continued without reassessment of the plan or potential new hazards. The first change occurred when the pump section had to be lifted back to deck when the cable ties broke. The second change occurred when the second worker was called in to assist with pushing the pump section. And finally, the third change occurred when the task leader handed over the trolley hoist remote control and went to assist pushing the pump section. Stopping, reassessing and revisiting the toolbox talk is essential in situations like these. Even seemingly small changes to a job can have significant impact on the risks of a job. When the job changes, stop and reassess task steps, hazards, and controls. Working over the sea introduces additional hazards, and therefore such work is rigidly controlled. One such control is fall arrest equipment. However, as scaffolding had been built around the worksite and the raw water pump was covering the only opening to sea, fall arrest equipment was not considered necessary. The work permit stated, approved scaffolding in place, so no work over the side. According to the applicable procedure, even with scaffolding in place, fall arrest equipment should have been used. The use of fall arrest equipment would not have prevented the accident, but would likely have prevented the fatal outcome. The use of fall arrest equipment is an essential safeguard when working over sea. Organizational barrier elements. The investigation found that everyone involved in the planning and execution of the task had the required regulatory training. However, still the involved personnel did not succeed in identifying and controlling the risks related to the lifting operation. Lifting operation is one of the key risks in an offshore drilling environment, and the right focus and competence on lifting is critical. The competency to identify, plan, and control lifting-related risk is essential to manage safety in an offshore drilling environment. Working over the sea with a 2.9 tons piece of equipment involves significant risk. Having to manually handle this heavy load under tension was a commonly accepted practice. So was not wearing fall arrest equipment. The investigation found that the risk tolerance for the job put the workers in harm's way and prevented them from mitigating against the risks posed by working over the sea. An out-of-harm's-way mentality, combined with recognition of essential safeguards, are critical elements to manage safety in an offshore drilling environment. As you have seen, on the 7th of December on the Maersk Interceptor, a number of barrier elements were ineffective, allowing the accident to occur and for it to have fatal consequence. Several key organizational learning points have been derived through the investigation into the accident. Strong barrier management and the presence of safeguards and capacity in our operation is essential for us to ensure that an accident like the one which occurred on the Maersk Interceptor does not reoccur in our industry.